Hello, everyone. I'm Yaxi. I'm a PhD student at Max Planck Institute for Intelligent System, and today I'll be presenting our work on provable privacy with non-private preprocessing. This is a joint work with my supervisors, Amatya and Bernard. So I'll begin with looking at this ML pipeline in practice. So the machine, the real world data is usually noisy and unstructured. So that cannot be directly used for training. What people usually do is they first preprocess their original data to get some somehow clean and also structured data, and then train their model on that data set. And people here also care about privacy. So instead of standard training, we do private training. And we hope that we have privacy. But this can be problematic because the private training BP guarantees only apply to the preprocessed data, but that cannot propagate to the original data set. Like the same level of privacy cannot propagate there. The reason there is also mentioned in today morning's talk by Matthew, like some of the preprocessing method that we used, like deduplication, scaling, or dimension reduction, actually uses information from the original data. And that introduced some sort of correlation to the preprocessed data set, and that causes additional privacy leakage. And one naive solution to this is just why not privatize the preprocessing methods? But this can be challenging in practice. First, you need a different technique for every preprocessing method. And also for some preprocessing method like PCA, your privatization can actually introduce an error that is proportional to the data dimension. And in that case, probably you are hampering the utility too much that it's better not just not do preprocessing at all. So in this work, we propose that probably we could just do non-private preprocessing and don't do any algorithmic changes to the whole pipeline. But instead, we kind of design a new way to account the privacy cost of the whole pipeline so that you can have some guarantee, you hope to have some guarantee that also holds to on the original data set. So yeah, a quick recap on the differential privacy. I think everyone here already knows it pretty well. It's just in our work, we use this running differential privacy, and here, oh, sorry, wrong direction. And here we express the privacy parameter epsilon as a function of alpha, so that we could characterize the privacy guarantee for any alpha greater than 1. And we note that running differential privacy also have the group privacy property. So basically it means if your data set differing by up to m data points, then your privacy parameter is amplified by at least a factor of m. And we know that this group RDP can be viewed as a naive method to account your the privacy of your non-private preprocessing, because if you already know that your preprocessing method will lead to a change of at most m points in the preprocessed data set, then you just need to amplify the private parameter by this equation. And as an example, I will talk about PCA. So now here we consider we have a non-private preprocessing PCA, and after that we do some sort of private training. It can be any other private mechanism, but here we have 2 neighboring data set. And then on top of this 2 neighboring data set, we compute their corresponding projection matrix. And then like we multiply the projection matrix with the original data set to have two preprocessed data sets. And now if we look at like just apply group privacy, then the privacy cost. So basically here, the goal is to compare, like if you want to like analyze the privacy of the whole pipeline, you want to compare the range divergence between the output distributions on this two preprocessed data set. So if we apply group privacy, then we just like count the number of different points in this two preprocessed data set, which in this case can be as large as the size of the data set n, which could be pretty bad. But we also observe that because PCA is a somehow stable preprocessing method. So if you just change one point in the original data set, the projection matrix won't change a lot in terms of Frobenius distance. So basically that's saying that in the two preprocessed data set, the Euclidean distance between like each point is actually upper bounded by a factor of 1/n under some assumptions on your data set if your data set is actually low rank and you are doing the correct PCA. So this observation, but like this thing, like this low Euclidean point-wise Euclidean distance is actually not utilized by the original privacy definition, because the privacy definition only concerns about like the number of points that differ in the data sets. So we think perhaps we could like define something else, another privacy that is defined under a smooth distance metric, and perhaps we could have better analysis there. So here we propose smooth RDP. So the definition of smooth RDP is basically it's very similar to the original definition of RDP, and it also appears in many other work. It's kind of related to metric DP, and it's also an instantiation of more general privacy framework like pufferfish privacy. But here we are basically not considering data sets with bounded Hamming distance. We consider data sets with bounded like L12 distance, for instance. So I think like in words, like the original definition kind of defines the stability against arbitrary perturbation on a fixed number of data points. But here we basically saying that we have stability against bounded perturbation on arbitrary number of data points. Because if you look at the example of PCA, every point changes, but like the change itself is very small. So we want to like quantify this kind of stability. And SRDP is not something that is very difficult to achieve. We also show in our work that under some assumptions, like the output, if the output function is Lipschitz or like the loss function is Lipschitz and smooth, then you have like your DP mechanism automatically satisfy SRDP. And here it's important to know that the SRDP parameters is of the same order in alpha and epsilon as the RDP parameters. So now we like with the definition of SRDP and the understanding that like each DP mechanism is actually SRDP as well, we could go to the main result. But before that, please bear with me and my notations. This is the last notation. We will introduce the sensitivity of preprocessing algorithm. So basically, for example, just now, PCA have very low sensitivity in terms of Euclidean distance. But like here, we want to capture that. And So here we define L2 sensitivity of the preprocessing algorithm as the point, like Euclidean distance between each point in the preprocessed version of two neighboring data sets. And then we also define L infinity sensitivity as the number of different points in the two preprocessed version of the original neighboring data sets. So with that, we have our main theorem, basically saying that if your preprocessing algorithm have L2 sensitivity delta 2 and L infinity sensitivity delta infinity, and the training algorithm is RDP, and we also like write SRDP as well, because we want the notion of function, then the whole pipeline is epsilon hat RDP, where epsilon hat is basically the sum, like, because the first term is like a constant, so like ignoring the technical details, epsilon hat is basically the sum of the RDP parameter and SRDP parameter. So I will, like, the proof is very simple, and the proof is basically an application of triangle inequality and directly by the definition of smooth RDP. So we have original data set, we have the preprocessing function computed with this two original data set, and we have the preprocessed data set. So here again, we want to compute the range divergence between the output distributions on this two preprocessed data set. But like we don't really know how to directly compute this range divergence. So we construct this synthesized data set, which consists of like parts from the two preprocessed data sets. And if you look at the upper two data sets, they kind of, they are neighboring data sets. So their range divergence is upper bounded by RDP. And the lower two data sets, they're like, by the definition of sensitivity of preprocessing, their L2 distance is kind of bounded. So they satisfy the definition of SRDP, so we can upper bound the distance, the range divergence between those two output distributions by the smooth RDP parameters. And then we apply one step of triangle inequality to get our bound. So with we apply our meta theorem on different preprocessing algorithms, and here is like a visualization of our result. So the blue line is the naive analysis with group privacy, and the green and the orange lines are from our analysis. But here, like, we have two lines. This is because this is kind of necessary, and it's because L2 sensitivity and L infinity sensitivity of the preprocessing function sometimes can be very large. And we need like some assumptions on the data set to make this sensitivity to be reasonably small. And we have so to overcome this assumptions on the data set and get unconditional privacy guarantee, we can probably use the proposed test release method to privately test whether the L2 sensitivity multiplied with L infinity sensitivity is small, and only release a result when that is the case. So some of the future directions of this work, because this work proposed a framework, but actually there are a lot of questions that we don't solve. First is like this efficient implementation for establishing unconditional privacy guarantee, because like PTR is impossible to computationally efficiently run it. So one solution could be like if you could design a method to kind of clip the original data set so that it always have low L2 and L infinity sensitivity, then you could potentially get unconditional privacy guarantee. And the other one is efficient implementation of PTR. And another direction is that we define SRDP under this weird L1 distance just for like our analysis, but perhaps this can be extended to other distance metrics. And yeah, thank you for your attention. And one quick notice, Amartya is looking for PhD and postdoc at University of Copenhagen.
We can take one quick question.
Yeah, I was just wondering, yeah, thanks for the nice talk. I was wondering, how do you handle methods that change the number of data points? Would it require, like deduplication, for example? Would it require a different definition of smooth RDP?
Because like we have this very weird definition of two sensitivity, where the first one is like the Euclidean distance between each point, and the second one is like the number of points that differ in those two preprocessed data sets. So for example, for deduplication, the first one can be infinity, like L2 sensitivity between each point can be like as large as the radius of your data set, but like L infinity sensitivity is upper bounded by like the number of points that are duplicates in your data set. So.
All right, let's thank.
Do you have any examples where you can implement PTR efficiently? These points?
Well, no. Sorry. I think that this is very hard, but I guess like design a method to like efficiently clip the data set so that I guess that would be easier, but I don't know.